Okay, thermodynamics. It's a branch of science which deals with the study of different forms of energy, and the quantitative relationship between them is known as the thermodynamics. Um, let's look into the importance of thermodynamics. So, if we are looking at the importance of thermodynamics, it helps to predict whether a given chemical reaction can occur under the given set of conditions. It helps in predicting the extent of reaction before the equilibrium has attained. It helps to deduce some important laws like laws of chemical equilibrium distribution law. Then let's look into the limitations of thermodynamics. It helps to predict the feasibility of process, but does not tell anything about the rate at which the process takes place. It deals only with the initial and final states of the system, but does not tell anything about the mechanism of the process. It deals with the properties like temperature, pressure of a matter in bulk, but does not tell anything about the individual atoms and molecules. Let's look into the few terminology, the terms involved in thermodynamics: system, surrounding, and boundary. The part of the universe chosen for the thermodynamic consideration is called a system. The remaining portion of the universe, excluding the system, is called surrounding. So, universe is nothing but a system plus surrounding. A system usually consists of a definite amount of the one or more substance and is separated from the surrounding by a real or imaginary boundary through which matter or energy can flow from the system to the surrounding or vice versa. The real or imaginary surface separating the system from the surrounding is called a boundary. Let's look into the open system. A system is said to be open system if it can exchange both the matter and energy with the surrounding. For example, if some water is kept in an open vessel, or if some reaction is allowed to take place in an open vessel, exchange of both matter and energy takes place between the system and surrounding. Example, presence of reactants in open beaker. Let's look into the closed system. So closed system means if a system can exchange only the energy with the surrounding, but not the matter, is called a closed system. For example, if some water is placed in closed metallic vessel, or if some reactions are allowed to take place in a cylinder enclosed by a piston, then as in the vessel is closed, no exchange of matter between the system and the surrounding can take place. As the vessel has conducting walls, exchange of energy can take place between the system and the surrounding. If a reaction is exothermic, heat is given by the system to the surrounding. If the reaction is endothermic, heat is given by the surrounding to the system. If the reaction is accompanied by decrease in volume, mechanical work is done by the surrounding and the system. If the reaction is accompanied by the increase in the volume, mechanical work is done by the system and the surrounding. Isolated system. Isolated system means if a system can neither exchange matter nor energy with the surrounding, it's called an isolated system. If a water is placed in a vessel which is closed as well as insulated, no exchange of matter or energy can take place between the system and the surrounding. Then let's look into the state of the system. The state of the system means condition of the system which is described in terms of the certain observable properties such as temperature, pressure, volume of the system. If any of these properties of the system changes, the system is said to be different state. That is, state of the system changes. The first and the last state of the system are called the initial state and the final state. These properties of a system are called state variables. So state function, a physical quantity is said to be a state function if the change in its value during the process depends upon the initial state and the final state of the system and does not depend upon the path or route by which this change has been brought about. For example, physical quantities which are state functions include the pressure, volume, temperature, internal energy, enthalpy, entropy, free energy, etc. So macroscopic and microscopic properties. If a system contains a large number of chemical species, that is atoms or ions or molecules, it's called microscopic system. Thermodynamics does not deal with the properties of the individual atoms and molecules, but it deals with the matter in a bulk. So properties of the macroscopic system like temperature, pressure, volume, density, melting point, boiling point are called macroscopic properties or thermodynamic properties. So an extensive property may become the intensive property by specifying the unit amount of the substance concerned. Mass and volume are the extensive property, but density and the specific volume are the intensive property of the substance or the system. Heat capacity is an extensive property, but a specific heat capacity is the intensive property. Thermodynamic equilibrium. So thermodynamic equilibrium, a system is said to be thermodynamic equilibrium if its macroscopic properties like temperature, pressure do not change with the time. Then what are intensive and extensive properties? Give example. Extensive properties means these are those properties which depends upon the quantity of the matter contained in a system. For example, internal energy, mass, volume, heat, capacity, enthalpy, Gibbs free energy are the extensive property. Intensive properties means these are those properties which depends only upon the nature of the substance and are independent of the amount of the substance present in the system. For example, temperature, pressure, viscosity, density, surface tension, freezing point, boiling point, mole fraction, etc. are the examples of intensive property. Let's look into what is the adiabatic and isothermal process. Isothermal process means when a process is carried out in such a manner that the temperature remains constant throughout the process. It's called isothermal process. When such a process occurs, heat can flow from the system to the surrounding and vice versa in order to keep the temperature of the system constant. Adiabatic process. When a process is carried out in such a manner that no heat can flow from the system to the surrounding or vice versa, that system is completely insulated from the surrounding. It's called adiabatic process. Then derive a relationship between the Cp and Cv. The relationship between the Cp and Cv are for an ideal gas. The molar heat capacity C at constant pressure is called Cp. At constant volume, it's called Cv. Cp is equal to delta H upon dt. Then you can take dt to the left hand side. Then Cp delta T is equal to delta H. Then we know that equation H is equal to means enthalpy is equal to internal energy plus PV. Then change in enthalpy is equal to change in internal energy plus change in PV. Then this is nothing. We know that PV is equal to RT. That's the reason delta U internal change in internal energy plus change in RT. Then change in internal energy plus R. R is a constant, so we are taking outside. So change in temperature. Then we know that the value, we can replace the value of delta H. The value of delta H is the Cp delta T, that is equal to delta U plus R delta T. Now we know that Cv is equal to delta U plus upon dt. We'll take dt to the left hand side. Cv into delta T is equal to delta U. Now we know the value of delta U, that means change in internal energy, that is nothing but a Cv delta T. Now we, in place of delta U, will add the Cv dt. Then Cp dt is equal to Cv dt plus R dt. We know that Cp delta T is called Cp and Cv delta T is called Cv. plus R when the temperature. Then Cp minus Cv is equal to R. R will be the universal gas constant. Let's look into the few statements of second law of thermodynamics. In a spontaneous process, the entropy of the universe is continuously increasing. So heat cannot flow spontaneously from cold body to hot body. It is impossible to construct a perpetual motion machine of a second kind. Heat cannot be completely transferred into work. In any engine, 100% efficiency is not possible. All naturally occurring process means spontaneous process always tend to proceed in the direction of the accompanied by the increase in entropy. Then concept of entropy. Entropy is a measure of degree of disorders or the randomness of the system. It is a state function denoted by S. Entropy increases with increase in the disorder in the system. The entropy of a gas is greater than the liquid. The entropy of a liquid is greater than the solid because of the randomness. Entropy of the system depends only on the initial and the final state and not on the path during the process. Change in entropy that we can denote as a delta S during a process is given by delta S is equal to S2 minus S1, where S1 and S2 are the entropies of the system in the initial and final states. Entropy change is always occupied by the absorption or liberation of heat. Entropy change in a isothermal reversible process is defined as the ratio of the amount of heat absorbed to the temperature T at which heat is absorbed. That is, delta S is equal to Q upon T. So unit of entropy is equal to joule per Kelvin per mole. So let's take the another one that is called spontaneous process and non-spontaneous process. Spontaneous process means a process that takes on its own under certain conditions when properly initiated is called spontaneous process. Example, flow of water from higher level to the lower level, flow of heat from a hot body to cold body, flow of current from higher potential region to lower potential region, combustion of fuel and the explosion, rusting of iron. These are the examples of spontaneous process. Then non-spontaneous process, a process that takes place only in the presence of an external head or agency is called the non-spontaneous process. Example is electrolysis. Then let's look into mention the criteria for the reaction to the spontaneous. So criteria for the equilibrium and the spontaneous process. For a reversible reaction, reactants will be converted into product, products gets converted into reactant. In this, delta Z is negative means the forward reaction is spontaneous. Delta Z means change in free energy is positive means the forward reaction is non-spontaneous. Change in free energy delta Z is 0 means the reaction is at equilibrium. So suppose delta H is negative, delta S is positive, then delta Z will be negative at all temperature, then it's spontaneous at all temperature. So delta H is positive and delta S is positive, then delta Z will be negative only at high temperature. That means spontaneous only at high temperature. Delta H is negative and the delta S is negative, then delta G will be negative only at only at low temperature. That means spontaneous only at the low temperature. Delta H is positive and delta S is negative. Delta G remains positive at all temperature. That means non-spontaneous at all temperatures. So let's take the numerical. Calculate the work done required to compress 2 moles of oxygen isothermally and reversibly from a volume of 10 decimeter cube to 5 decimeter cube at 250 Kelvin. Here gas constant R is equal to 8.314 joule per Kelvin per mole. So here what is given, volume is given, V1 will be 10 decimeter cube, V2 will be 5 decimeter cube, and temperature is 270 Kelvin and N is equal to 2. So work done is given by, then W is equal to minus 2.303 into N RT log V2 upon V1, that is equal to minus 2.303 into 2 into 8.314 into 270 into log of 5 upon 10, that is equal to 3112.486 joule per mole. Let's take one more numerical. So calculate the work done when 3 moles of an ideal gas compressed reversibly and isothermally from the pressure of 1.5 into 10 to the power of 5 newtons per meter to 4.5 into 10 to the power of 5 uh, 5 newtons per meter at 298 Kelvin, then R is equal to 8.314 joules per Kelvin per mole. So we can apply, W is equal to 2.393 into nRT log of P1 upon P2. W is equal to 2.303 into 2 into 8.314 joule per Kelvin per mole log of 1.5 into 10 to the power of 5 and Newton meter square 2 upon 4.5 into 10 to the power of 5 newtons per meter square. This on simplification, W is equal to 18.2644 joule per Kelvin per mole. So let's take a few more numericals. So this is calculate the work done when 2 mole of an ideal gas expands isothermally and reversibly from 2 decimeter cube to 12 decimeter cube at 25 degrees centigrade. R is equal to 8.314 joule per Kelvin per mole. Then W is equal to 2.303 nRT log of P1 upon P2. Then W is equal to 2.303 into 2 into 8.314 joule per Kelvin per mole into 298.15 Kelvin log of 2 decimeter cube upon 12 decimeter cube. Then this on simplification, W is equal to negative 28882.76 joule per Kelvin per mole. Let's take one more numerical. So calculate the work done expansion of the 1 mole of an ideal gas at 25 degrees centigrade under isothermal condition. The pressure being charged from 1 atmospheric pressure to 5 atmospheric pressure. So the given value N is equal to 1 and mole 1 mole and R is equal to 8.314 joule per Kelvin per mole. Temperature T is equal to 25 plus 273, that is equal to 293 K. Then we can apply W is equal to 2.303 nRT log of P1 upon P2. So that is equal to 2.303 into 1 mole into 8.314 joule per Kelvin per mole into 298 Kelvin log of 1 upon 5. So that is equal to 5705.848 into log of 1 upon 5. So that's on simplification minus 3988.38 joules. So let us take one more. So what is the maximum work obtainable from the isothermal expansion 3 moles of an ideal gas at 27 degree from the pressure of 4 atmosphere to 1 atmosphere. Also calculate the quantity of heat evolved in the process. To calculate the maximum work obtainable, given is N is equal to 3 moles, R is equal to 8.314 joule per Kelvin per mole, and the temperature is equal to 27 plus 273, that is equal to 300 K. Then pressure 1 is equal to 4 atmosphere, pressure 2 is equal to 1 atmosphere. Then W is equal to 2.303 into nRT log of P1 upon P2. So values adding and then substitute simplifying will get 10.37392 per kilojoules per mole. So this will be another numerical one, and this will be one more. Use the Gibbs-Helmholtz equation to show that 2 molecule of carbon monoxide plus oxygen gives rise to carbon dioxide in spontaneous at 275 Kelvin and 1 bar. Then delta H naught is equal to minus 566 kilojoules per mole. Delta G naught is equal to minus 514 kilojoules per mole. Then integration form of Gibbs Helmholtz equation, delta G upon T2 minus delta G upon T1, that is equal to delta H in 1 upon T2 minus 1 upon T1. Then delta G2 upon 375 K minus 514 K joule per mole upon 298 K, that is equal to minus 566 kilojoules per mole. It's nothing, 1 upon 375 Kelvin minus 1 upon 298 Kelvin. This on simplification, delta G02 is equal to minus 501 Kelvin. This negative value indicates the spontaneous, right?